I'm going to talk about the paper Quantum Algorithms with Cut Queries, which is joint work with Miklos, Santha, and Shengyu, Zhang. A common model for studying graph algorithms has been what might be called local query models. So for example, the adjacency matrix model, you can query, ask the question, is there an edge between vertex I and j, and get the answer, or the adjacency array model, where you can query the degree of a vertex v, or ask what is the ith neighbor of a vertex v. So in both of these cases, we're just getting information about a single edge slot or a single vertex. So in contrast to this, there are what might be called global query models, where with a single query, we can get aggregated information about many edge slots or many vertices. And these models have been becoming increasingly popular over the last 5 years. And there's many different global query models that have been studied. Just to throw out some names, there's cut queries, additive queries, independent set queries, linear queries. And each of these has motivation coming from a different source, but some sources of motivation include streaming algorithms, applications to DNA sequencing, and applications to submodular function minimization. So in this work, we're going to study cut queries. So let me define what a cut query is. Let AG be the adjacency matrix of a simple graph G. So in a cut query to G, we can ask any Boolean vector X and receive the answer X transpose AG times 1 minus X. So in other words, if X is the characteristic vector of a set S, we can ask the set S and we get back the number of edges from S to the complement of S. So in other words, the number of edges crossing the cut defined by S. So we study quantum algorithms for 2 different problems using cut queries. And those are the problems of learning a graph, so just learning all the edges of a graph, and determining if a graph is connected or computing a spanning forest of a graph. So let me talk about these 2 problems in turn. So for learning a graph, classically, if the graph has m edges, then up to log factors in cut queries is necessary and sufficient to learn the graph, even by a randomized algorithm. On the other hand, we show that there's a quantum algorithm that learns a graph with m edges using only around square root of m many cut queries. So here we have like a quadratic difference. For connectivity, there's a very nice paper by Rubinstein, Schramm, and Weinberg that gives a randomized algorithm that even beyond connectivity, it actually computes the minimum cut of a graph with n times polylog many cut queries. And this result is essentially tied to log factors. And the lower bound is even shown for the simpler problem of just determining if a graph is connected or not. So from work on communication complexity, we actually know that it takes at least n over log n many cut queries for a randomized algorithm to tell if a graph is connected or not. So another reason why these results are interesting is the relation to submodular function minimization. So the cut function, that is the function that on the set S returns the number of edges in a graph from S to the complement of S, is a submodular function. So determining the minimum cut of a graph with cut queries is an instance of finding a non-trivial minimum of a submodular function with evaluation queries to the function. So non-trivial minimum just means that a minimum which is not the empty set or the set of all vertices. So this randomized lower bound of n over log n, that's actually the best lower bound that we know in general on the randomized complexity of finding the non-trivial minimum of a submodular function. And These results are actually what started our paper. So we were interested in quantum algorithms for submodular function minimization. And we kind of started with this specific case of the minimum cut problem, and even the special case for which this lower bound was known, connectivity. And we were trying to show a similar lower bound in the quantum case. That didn't work out too well, and eventually we came up with this algorithm that actually there's a quantum algorithm that can output a spanning forest after only poly-logarithmic cut queries. Okay, so we have a bound of something like log n to the 8th many cut queries. So for this problem, we have a separation of polylog versus nearly n for the quantum versus randomized complexities, determining if a graph is connected with cut queries. Now let me say a few things about how the proofs work. So for this high-level overview, instead of cut queries, I'm going to talk about a less restrictive kind of query, which we call matrix cut queries. So here, for any two Boolean vectors x and y, you can query x and y, and you get back x transpose ay. So this kind of has all the interesting ideas. This case has all the interesting ideas of the proof. And then there's one more little trick that we use to go from matrix cut queries to cut queries. Okay, so our algorithms basically break down into a quantum part and a classical part. So the quantum part is the following. We show that there's a quantum algorithm that for any Boolean vector y can compute the n-dimensional vector a times y with order log n many cut queries. Okay, so after order log n many cut queries, you actually get written down on a piece of paper this n-dimensional vector a times y. So this is quite a powerful tool, and we show how to do this with an extension of the Bernstein-Vazirani algorithm. So Bernstein-Vazirani is one of the very early quantum algorithms, and we just generalize it a bit to give this result. Okay, so with this quantum part in hand, the rest of the paper is actually looking at classical algorithms that are able to use these matrix vector queries. Okay, so let me describe how the classical algorithm with matrix adjacency matrix vector queries we're able to learn a graph. So we basically use two different tricks for this. One to do with high degree vertices, one to do with low degree vertices. So for high degree vertices, we observe that with a single query, we can learn a single matrix vector query. We can learn the neighborhood of one vertex. So say that we want to learn the neighborhood of vertex 1, then we let y be the vector 1, 0, 0, 0, 0, 0, this first standard basis vector. Then from a times y is just the first column of a. So from that, we learn the entire neighborhood of the first vertex. So that was just one matrix vector query. For the second part, we used ideas from compressed sensing, and that is that if A has at most D1s per row, then we can actually learn the entire matrix A with only D log n many matrix vector products. So essentially, if we just choose the y's randomly, then from the D log n many random products, A times Y, from all that information, we can reconstruct A. So this is the essential idea behind compressed sensing, which is that sparse vectors can be learned from a few random inner products. Okay, so we use the first trick to learn high degree vertices and the compressed sensing part to learn low degree vertices. And when you balance the cost of these two procedures, we get these nearly square root of m algorithm to learn a graph with m edges. Okay, so for connectivity, we similarly just design a classical algorithm with matrix vector queries to the adjacency matrix that makes polylog many queries and can compute a spanning forest. So this proof is actually similar to work that was originally done in the context of sketching, so work by An, Guha, and McGregor, which developed a nearly linear size sketch of a graph from which you could determine if the graph is connected or even compute a spanning forest. And later work by Sun et al. Kind of rephrased the work by An, Guha, and McGregor in the context of query algorithms with matrix vector queries. But that algorithm actually works not with the adjacency matrix, but with the vertex edge incidence matrix. Okay, so our algorithm kind of follows a similar procedure, but with matrix vector queries to the adjacency matrix. And this is based on a classical algorithm for computing spanning forest, Breuil's algorithm. So it's kind of a parallel version of Breuil's algorithm. Okay, so that's just kind of a short, high-level overview of our results. Thanks for watching.
Good morning, everyone. My name is Changpeng. I will talk about quantum algorithms for learning graphs. This is based on a journal work with Ashley Montanaro. In this talk, by learning a graph, I always mean identifying all the edges of this graph, and we will consider this problem in 3 different models. Actually, I will mainly focus on the first and the third model, since the main idea to the second model is very similar to that of choice talk. The first 2 models arise from wide applications in biology, and there are many researchers in the classical case, but there are few results in the quantum case. And our paper is an attempt to show the advantages of quantum computers in solving this kind of problems. Okay, let's see what we have. We suppose we know the set of vertices, and in the first model, we have an oracle to query the vertices. And in the third model, we can access to the graph state. It corresponds to the graph we want to learn. As far as goes, the first one is quite obvious. We try to use as few queries as possible. The second goal is we hope at the end the query complexity can only depend on the number of edges. Since in this kind of applications, usually the number of vertices is much larger than the number of edges. Okay, let's see the first model. In this model, the oracle, you can query any subset of the vertices, and it returns 0 or 1 depending on whether this subset contains any edges. First, let's see our main results. Then I will explain some basic ideas. Okay, first, if we know nothing about this graph, we just know it is a graph, then there is no speedup. If we know the graph has at most m edges, then there is a more distant speedup when m is much smaller. As you can see, we have an upper bound and we also have a lower bound. It seems our quantum algorithm is almost tight up to a log factor. If the graph has more structures, then the speedup can be much larger. For matches and cycles, and there are still some gaps, and for learning stars and clicks, our quantum algorithm are already optimal. Okay, let's see the main ideas for learning a graph with m edges, the matching and the cycle. The quantum algorithm for learning stars and clicks are quite straightforward from our technique we use here. Okay, first, we try to decompose a set of vertices into a disjoint unit of k subset. Here, we hope each VI includes no edges, and we also hope this k can be as small as possible. So this is just a k coloring. So how can we do this just using an oracle? So the idea is we first determine a probability p, then we put each vertex into this subset S with the probability p independently. Now by the unit bound, it's not hard to prove that the probability p such that the probability such that S includes no edges is at least 1 minus MP squared. So for instance, we can just choose P as 0.1 divided by root n. Then with probability at least 0.99, we can find V1. After we have V1, in the remaining set of vertices, we can use a similar idea to find V2 and so on. At the end, you will see this n, this k is close to root n log n. Actually, this is almost optimal, since, as you know, for a complete graph, you need at least root n different colors. Next, we have to find the edges between VR and Vj. The first step greatly simplifies this problem. The main idea is we can decompose this, we can reduce this problem into a combinatorial group testing problem so that we can use the Belovs quantum algorithm to solve this problem. Yeah, the procedure is a little lengthy here. Maybe I don't explain it here, but this is the best idea. One thing I want to say is Belovs. Belovs, he give a coefficient quantum algorithm for this combinatorial group testing problem. It is quadratically faster than the classical algorithm, and his algorithm is optimal. Actually, in our paper, we also give a time-efficient quantum algorithm for this problem. The time complexity is only a little worse than the core complexity up to a log factor. Okay, now let's see how to learn an Allen graph. I will give the definition of graph state in the next slide. Here, you just need to know we can access to a graph state and it corresponds to the graph we want to learn. As usual, let's see our main results first. Okay, first, if it is just a graph and we know nothing about it, then there is a quadratic speedup. If we know that this graph has at most m edges, then our quantum algorithm doesn't show a speedup. But it doesn't mean there is no speedup. It's just we didn't find one. If the graph has more structures, then the speedup can be exponential. Now let's see the main idea. Maybe you're already familiar with the definition of graph state. If ij is an edge, then we apply the control z to the I and j's qubit in the superposition. It's quite easy to check this graph state is invariant and this kind of operators, and they are called the stabilizers of the graph state. Yeah, nu is the neighbors of V, and V is the neighbors of V. One technique we use to learn an graph state is called Bayer sampling. It was introduced by actually Montanaro a few years ago. And each Bayer sampling returns a uniformly random stabilizer of the graph state. So it is just a random product of this kind of Pascal stabilizers. And we can express this in this kind of form. S is a subset of the vertices. So we can view this S, this capital S, as a bit string of 0 and 1. 1 means U is in S and 0 means U is not in S. Maybe it's not so obvious, but this quantity here, this quantity equals the inner product of the U's row of the adjacency matrix and the bit string of S. Since U runs over all the runs over the set of vertices, so actually each Bayer sampling returns a bit string A times S, modulo 2, for a random S. Here A is the adjacency matrix. So if we use K samples, then we will obtain a Boolean matrix B and the matrix A times B, modulo 2. Now we can just solve A by solving a linear system if we choose K properly. Okay, our first result is like this. If we know this graph G comes from a family of graphs, then we can identify G uniquely by using log of size of F copies of the graph state G. So for instance, if we know G is a graph with at most m edges, then this quantity is just m log n squared over m. Maybe you're familiar with this kind of quantity since by information theoretical arguments, this is a lower bound for learning graphs in the classical case, and this result shows that it is an upper bound in the quantum case. Actually, we also have a lower bound in the quantum case. It is the root of this quantity. So it means maybe there is a quantum speedup for learning graphs in this case. Our second result is about learning boundary degree graphs. The main idea to obtain this result is still based on bare sampling. But the procedure is, maybe a little technical, but the algorithm looks quite intelligent. You see, if the vertex V has degree at most D, then this algorithm outputs all the neighbors of V and tells us that V has degree at most D. And if the vertex has a degree larger than D, then the algorithm just output the degree of this vertex is larger than D. Okay, another thing is if we know this graph G comes from a given bounded degree graph, then this algorithm can be made time efficient. Okay, thanks very much for your attention.
Okay, thanks a lot for the talk. And yeah, at this point, I just want to again refer to the active Slack channel. So one question I was asking there is for the first talk, where this power of 8 in the order of log n to the power of 8 comes from, and I don't want to like read all the text from the Slack channel, but there's a ongoing discussion there. And maybe I can directly ask another question to the second speaker, to Changpeng. So are you here still? Maybe you can quickly unmute yourself in the Zoom meeting. Yeah, right. So so since you talked about graph-based, yeah, I mean this graph-based quantum circuit, so to say, or my question would be, can this be also used as a kind of a simulator of let's say of a quantum circuit, right? Because there are methods in this graph-based simulation or measurement-based simulation of quantum circuits. So I'm just curious about the connection between what you presented, which was more like, I guess, graphs, generally graphs in the mathematical sense, and this more applied direction.
I'm not so sure about this since it seems our paper just focus about how to learn a hidden graph, and we just want to know what is this graph when we have some oracles. So I'm not so sure about the connection between our results to the simulation of quantum circuits.
Okay, yeah.
At least I don't think so right now.
Okay, right. Maybe I can look at some more questions in the chat. So by the way, what Troy Lee responded regarding this power of 8 scaling. So yes, this is related to, I mean, at least one factor of log n would be resulting from Borowska's classical spanning forest algorithm. And then you can basically, so it's kind of interesting to follow the discussion. You can assemble, so to say, or collect these log n factors, which would in the end, make up this polynomial log n to the power of 8 result of the first talk. Maybe Changpeng Shao, can you maybe illustrate a bit the connection between Troy Lee's talk and your results, so to say? So I guess you're building on top of his results.
Yeah, that's right. Since I didn't discuss the practical model in the talk, the reason is in the practical model, we use some similar technique to Troy's paper. That is, for instance, one technique they used is we have the adjacency matrix, and for any y, we can output A times y very efficiently in our quantum computer. And actually, we also use this kind of technique. And also another technique we use is decompose the vertices into high degree and low degree parts, and then learn each part separate. And I think this technique is also very similar to that technique.
Okay. Mm-hmm.
Yeah, actually, I think, yeah. Also, since another reason I didn't mention this practical model is because the main idea is also very similar to the graph state model in the so maybe I think it's very similar.
Okay, yeah, thank you. Okay. Right, I'm still watching the Slack channel here. Is there more questions coming up? Okay, I just read the question which was posted in the chat. So talk mentioned exponential speedup on a couple graph types, but skipped really fast that I could barely see. Maybe you can just show that slide once more and go into detail a little bit. I guess this is, I'm not exactly sure whom this is addressing. So
okay, maybe I say something.
Is this addressing Troy Lee or you?
Yeah, okay. Okay, maybe Charlie can answer this question in the Slack.
Yeah, okay, yeah.
Okay, I just maybe say a few things here.
Right, and since okay, just to as a comment, I mean, since talks are recorded, right, you can always just go to the video if a slide was too fast, right? You can just go to the recorded video and then yes, stop there, so to say, when you want to watch the slide. Okay. Mm-hmm. Okay, so I think since we since we reached the end of the first slot, I would just say that remind everyone that there will be a roundtable at 12:30 with the speakers for more detailed discussions and one-to-one discussions, right? And now we will switch over to the second talk of this session. So